Talking to high availability at Braintree. I'm a software developer. Feel free to ask me questions about Braintree after the conference or after the talk if you're interested in the things that I don't cover. So Braintree, we're a payment gateway. What that means is we essentially have software to process payments through mostly online or mobile applications. Generally, we deal with credit cards. So these are some of our merchants. So the idea with Braintree is like if you go to github.com and you want to pay for service, you type in your credit card info, you hit submit. That credit card info stuff comes to us, and we do all the payments related stuff. So we charge the cards, we move the funds at night. We do tokenization, so you can get back a token and charge the card later without having to store credit card details. So pretty much all of that, all of the payments related stuff behind these sites essentially is us. So the question, why is uptime important to us? We do roughly $10 billion in processing at our current estimates. That comes out to be about $19,000 a minute. So downtime is extremely costly for our merchants. And besides just like the raw cost for them and for us, obviously we take fees on this stuff. You may not know that a lot of those merchants use Braintree. So if we're down and you go to check out at a site, you may get an error. You may get like your credit card's not valid when actually it is valid. So we would make those sites kind of look bad because we're behind the scenes. You don't know that those sites use Braintree, most of them. We're not like PayPal where you have like the pay with PayPal button. We're more of like a silent partner. So downtime just makes everyone that we work with look bad, and it loses them a ton of money very quickly. So we care very deeply about uptime. So people talk a lot about uptime. Not a lot of people know exactly what the numbers kind of mean. So this chart from Wikipedia kind of trimmed down is pretty interesting. People kind of throw out 5 nines as a target. 5 nines is extremely difficult. It's 5 minutes a year. So if your primary database crashes and it takes some kind of manual work to bring it back up, and that takes 10 minutes, let's say, you've blown 5 nines for the whole year. 26 seconds a month. It's almost nothing. I would say at Braintree, we're probably closer to 4 nines. We strive for 5, but probably closer to 4. Although our uptime is actually really hard to measure due to some of the stuff I'm going to talk about later. Just we have a lot of kind of pieces and players involved, and so it's hard to know exactly what our uptime is for different merchants. But yeah, this just to give you an idea, like 5 nines is unbelievably difficult. OK, so this talk I'm going to cover 3 main causes of downtime. Planned maintenance, so this is we know we need to do something to the site or to our infrastructure. We're going to do something on purpose. There's unplanned failure. Parts of our infrastructure fail or things that we depend on will fail. And then basically people mistakes, people doing stuff that they shouldn't have done, causing problems. OK, so planned downtime, this is reducing our maintenance windows. So for us, the biggest thing we do, the biggest maintenance window we have is code deploys. We're a fast-moving company. We're constantly deploying new versions of things. These are typically kind of maintenance windows. So Braintree, the main gateway started as a pretty typical Ruby on Rails app about 4 years ago. So it ran on MySQL. It used Apache Passenger, just kind of the typical stuff you would have seen from a few years ago. So the way we would generally deploy at that time is we would put up a maintenance page. We would deploy our code out, switch it all over to the new stuff. We would run all of our database migrations. So again, like a fast-moving company, fast-moving code base, we would constantly change our database schema. And then we would take down the maintenance page. So for this, we're basically down for the entire time that we're deploying the code, which is very quick, just moving symlinks mostly, and then running database migrations. And those, as we would grow, would get slower and slower over time. And so at a certain point, like these database migrations were just overwhelming. Like we were down for noticeable amounts of time. It was a really big problem. So one of the first things we did kind of in the early days was we switched from MySQL to Postgres. So Postgres, DDL migrations are extremely fast. You can add, rename, edit columns extremely quickly. In MySQL, MySQL would copy the entire table if you wanted to add a column. And so as your tables start growing and getting very big, the time to copy a table gets larger and larger until it's minutes. I mean, I've been on projects where MySQL migrations took hours. And your site is basically unusable at that time. So Postgres, on the other hand, extremely fast. We're talking millisecond operations for all this stuff. Similarly, you can also add indexes in Postgres really quickly. So Postgres gives you this keyword concurrently, which lets you add indexes without locking tables. With MySQL, we would try to add indexes. The tables would lock. The site basically becomes unusable. Postgres, largely unnoticeable. It takes a little bit extra CPU because it does like 2 scans of the table. But you can do it while the site's up and with pretty much no impact. And then the other big one was Postgres lets you wrap DDL migrations in a transaction. So we use Rails migrations. If your migration has 10 statements in it and the first 5 run successfully and then the 6th one fails, your database is in a pretty bad state. And you have to usually either manually try to roll it back or manually finish the migration to get to a state where you can run the code again. And so with Postgres, you can wrap the migrations in a transaction. If it fails in the middle, the whole thing rolls back. You're back to the previous state. You just put back the old code and keep going. So you're not in this state where you can't run the app anymore. And this, I actually did a whole presentation on just this topic. If you're interested, you can check out the slides. The migration wasn't super simple, but it's very doable. And we did it with very little downtime as well. OK, so given that, we moved to Postgres. Now our new deploy process is, while the site's up, while we're running kind of the old stuff, we add new tables and columns. So we kind of get ready. So like I said, these are super fast, millisecond operations. We get all the new schema stuff ready. And then we roll out the code server by server. So at an app server at a time, we put out new code, and we restart. So again, no downtime here, because we're doing one at a time. And then when the site's fully on the new code, then we can go back and add all the indexes, all the things we discovered with how new usage patterns work. And we go back and do that. And this has no downtime, right? We've done everything we can while the site's up. We put out the code server by server, no downtime. So this is kind of what it looks like for the migrations in Rails. So people are familiar with Rails. Rails gives you a DB migrate task. We basically added 2 new ones, migrate pre and migrate post. We use the same Rails code. We just pointed different folders. So now any migrations you put in the migrate pre folder will run before the code is out, and any migrations in the post will run afterwards. So it's pretty straightforward. OK, so one problem with this is that Rails caches columns. So when Rails starts up, it interrogates the database, and it caches the set of columns for every table. So what this means is you can't actually delete columns. So even if your code is no longer using a column, if you try to delete it, Rails will still send the same statements with the column in it oftentimes. And then you'll get these errors like column does not exist. So what we wanted was basically a way to tell Rails to forget the column. And so we added it. So it looks like this. So on our models in Rails, we just add a method called deleted columns. You list out all the columns you no longer want to use. This is implemented behind the scenes with some kind of alias method chaining stuff for people that are familiar with it. Basically, we overwrite the columns method in Rails in active record, and we strip out all the columns you told us to delete. So now, after we deploy, we put out the new code with this deleted columns code in there. Rails, when it restarts, it doesn't even know about the column, doesn't include it in any queries. And then we can go in the post migrations, we can then drop old columns that we're no longer using. And usually, we don't usually drop columns right away. We usually delay a release, giving us the ability to roll back one. So let's say we're no longer using a column. We'll add the deleted column line, deploy that, and then in the next release in the post migration, we'll drop the column. So we can always roll back at least one release. Because if you drop the column right away and you try to roll back, then you have old code which needs a column, and the column's not there. So we generally delay one. OK, so one thing I talked about a little bit but didn't really go into yet is that we actually run multiple versions of the code at once. As we're doing the server by server deploy one at a time, for that several minutes that we're doing that, we have the old code running on some app servers and the new code running on others. It turns out that that's actually fine for most features. Like most things we do are additive. Some new feature will show up maybe and not show up for like a moment and come back, or we're changing a backend integration and we'll start sending a new flag, but some requests won't have it yet. It turns out it's generally OK. For places that it's not OK, we use a lot of feature switches. So we have the ability to turn things on for one merchant or kind of globally. So with a lot of new features, we'll deploy it dark. We'll get it all out there, make sure the site is fine otherwise. And then we'll turn on a feature for just one merchant, and we'll watch it. So we'll work with like beta merchants for different features. And then we can watch the traffic, watch how it's doing. We can turn it back off if there's a problem. If it's going well, we turn it on for more merchants. And eventually, we roll it out across the board. For things that aren't really merchant-specific, that are more global, we just have global switches too. So again, we can roll out features dark and then just turn them on globally. And then once things have been out for a long time and we know we're not going to turn them back off, we'll just remove the switches just to kind of clean up. So we do this a lot. We feature switch almost all new features just as a way to reduce risk as well. Like we can put things out, know that they won't affect anything, and then turn them on and watch them. Thus, also preventing the ability, the need to roll back. Because rolling back is pretty large, pretty large hammer essentially to hit something with. So we want to just use switches to turn things on and turn them back off. So what I've described is pretty much the way we do 95% of our deploys today. We do them almost all server by server. But there are some limitations with that approach. So a big one is column renames. So we can add columns in a pre-migration. We can now drop them in a post-migration with the deleted stuff. But you can't really rename columns. It's really hard to rename a column while the site's up because you'd somehow need the code to know about both the old name and the new name and then understand when to switch over. And it's really difficult, so we just generally don't do it. There's other maintenance tasks like database failover. So what I've showed works really well for code deploys. But if we need to take down our primary database for security upgrades or something like that, nothing I've really talked about handles this case. And then just other infrastructure. Similar to databases, there's lots of work we want to do in our data center that requires us moving, taking a primary load balancer out or taking a primary database out, and nothing really covers that. So what we essentially really wanted was a way to pause traffic, something that would allow us to do other types of issues, other types of maintenance without downtime. And so that's what we built. So this is what our architecture looks like today, heavily simplified, obviously. So we have we have a load balancing layer coming into multiple Apaches. I've drawn 2 here. There's more than 2. And then it goes to something called the proxy, which I'll go into. This is something we wrote. And then the proxy feeds into a Redis queue. So we use an in-memory queue in Redis. And then we have the dispatchers reading out of Redis. So the piece to note here is we basically put a Redis queue in the middle of our request processing. So the proxy, it stands for Braintree proxy. We're not very clever about naming. So it's a Python Tornado app. So at the time we wrote this, it's been a few years now, we kind of looked around for what to write it in. We're generally pretty polyglot at Braintree, and we wanted something that was very efficient and just kind of easy to write. So what this app is doing is it's taking every request, it's just shuffling requests around. So we like the idea of something evented because it's going to hold tons of open connections. It's just moving data around. It's very lightweight. At the time we looked, Tornado just seemed really nice. It was running with FriendFeed and Facebook. It was running in production. It has some really nice built-in testing stuff, so we decided to kind of go with it. So like I said, it accepts web requests from Apache, and then all it does is it bundles them up and puts them into a Redis queue. So it takes the body, the headers, pretty much everything that comes in that request, puts it in a message, and puts it in Redis. And then on the way back, it reads out of a response Redis queue, and then it responds back to the web request. So it's just feeding into Redis and then responding back out. So the dispatchers on the other side, so these are lightweight rack adapters. So for those that don't know, rack is like a Ruby web server framework, I guess. It's like pretty much all the Ruby web servers now adhere to a rack interface. So the dispatcher is a rack interface that basically integrates with Rails. So it takes the request from Redis, and then it processes them through Rails. So we still use Rails. We just do it via a queue instead of a web server. And then it takes the response, after it gets the response from Rails, it puts it back into Redis, and then it goes back out to the proxy. So the dispatcher part looks like this, essentially. It's a Ruby script. We basically load Rails root config environment. So at this point, we have Rails loaded. We have all the code available to us. And then we build our own rack app, but we use the action controller dispatcher. So we're building a rack app, but we're really using all of Rails code, right? We don't really want to rewrite a web server, essentially. So we're going to use all of the Rails stuff. So then in a big loop, we just pull the request out of Redis, and we build a rack request. So a rack request is just a big hash of pretty much everything rack needs. Here I've shown 2 elements, but there's like 10, including the URI, body, headers, pretty much everything. And then the last line you see there, we just do app.call. So this processes through the whole Rails stack. We go through all the middlewares, pretty much everything that Rails normally does for a web server, we just do through this rack adapter. And then once we get the response, we just turn that back into a string and then put it back in Redis. So we put back the status, the body, we put the headers, a bunch of other stuff, and we just send it back out. So that looks like this again. So now, when we want to suspend traffic, all we have to do is stop dispatchers. So we stop the dispatchers. The entire top half of the stack is still working. Requests are coming in, they're in queuing. There's just nothing processing them. And since the dispatchers aren't running, nothing's using the database, nothing's using like our search servers. Pretty much everything on the bottom is unused. So we can do any kind of maintenance we want. We can push out new code, we can rename columns, we can do database failover, pretty much anything we want. And then when we're done, we just restart the dispatchers, they clear out the queue, and everyone's happy. So the users will see long requests, but they won't see failed requests. And in general, we feel like that's a better trade-off. Today, people have gotten pretty conditioned. Like if you hit submit on a payment form, sometimes it's going to take a little while. So instead of seeing a 2-second request, you'll see a 20-second request. but you'll still get the proper request, or the proper response, and that's pretty important. And so as long as we can keep our maintenance to around 20 or 30 seconds, that's kind of our window, we can just do everything without getting timeouts. So another nice thing is we provide client libraries. So people integrate with Braintree through our client libraries. So we know what the timeouts are. We can control the timeouts. We can make sure that the amount of time we keep the dispatchers down for is less than the timeouts at the top level. We control the proxy timeouts. So we basically know exactly how long we have at every step in our stack to do the kind of work we need to do. And so we basically can do a lot of work in 20 to 30 seconds. Like I said, any kind of failover. We use this technique to switch data centers at one point, where we actually move traffic from one data center to another with a pause and without losing traffic. So it works pretty well. So just to summarize this section, we basically do pre and post migration. We do as much work as we can while the site's up, reducing risk, also no downtime. And then we do rolling deploys for nearly every deploy. We roll out code server by server, restart things, keep the site up as much as possible. We use Postgres because it's really fast at doing a lot of database work. We really like Postgres in general. It's a great database. And then for everything where we can't do that, we use the proxy. And that's every kind of maintenance where we actually need to just pause traffic to get something larger done, essentially. OK, so that's planned failure. That's how we do the stuff we know we need to do. Then there's a whole set of unplanned failure. Right? Servers fail. Networks go down. It's pretty common. Essentially, the unexpected happens. And all we can really do is do our best to be resilient. So we try to build resilient systems such that it can handle even unexpected issues. So start with server failure. Pretty typical way to handle server failure is load balancing. In this case, we're no different. We build our own load balancers, though, so that is actually pretty different. In general, at Braintree, we like components that are simple and easy to understand. So we tend to shy away from black boxes. And so load balancers are a giant kind of black box appliance. They work well for some people. People love to complain about them. I mean, if you hear lots of horror stories about like F5s and stuff like that. So we prefer just to kind of build our own. We understand it at every level. We can tune it for availability, for security. We can tweak it to our needs. So we just really like to control it. So what we use is LVS or IPVS. This is the Linux Virtual Server Project or IP Virtual Server. It's basically kernel level routing. So our load balancers are just Linux servers. Traffic comes into them, and then via kernel level rules, the traffic gets routed to other backends. So it's pretty simple. We manage a cluster of them with Pacemaker, so it handles failover if a load balancer dies. And then we have two components that we wrote called Big Brother and Litmus Paper, and I'll go into these in a moment. So this is the diagram of what it looks like. So traffic comes in either externally or internally. We load balance a lot of internal services. It goes to a virtual IP living on one load balancer. Each load balancer has many IPs for all the different services. And then the load balancer forwards the traffic to backend, in this case, Apaches. And the piece to note is that Big Brother runs on the load balancer, and Litmus Paper runs on the backend. So Big Brother, it's a Ruby app we wrote. Like I said, it runs on the load balancers. Its job is just to check the status of the backends. So every second, it's just polling backend servers, getting the status of how they're doing. And then it updates IPVS rules. So if it discovers a backend's down or not responding, it updates the kernel level rules to change the routing such that new traffic won't flow there. And so it's just doing that constantly. It's just in a big loop. And Big Brother's open source. You can check it out on our GitHub. So on the other side is Litmus Paper. Litmus Paper is also a Ruby app. It's the piece that Big Brother is querying via HTTP. And the idea is with Litmus Paper is it's a consistent interface that Big Brother can query. So it runs on all of our backends, and it returns a health level. And its job is to kind of map between whatever it needs to do to that health level. So for an Apache server, it probably just turns around and curls Apache. And if Apache's up, then it says I'm up. And then it combines that with system level info. So if the load is high, but Apache's up, maybe the health isn't 100, it's 80. If it's totally down, the health is 0, that kind of stuff. So Litmus Paper just figures out what it needs to do for that server, for that type, and it returns a health level to Big Brother. And this is also open source, so you can check it out. So there's the diagram again. So like I said, Big Brother is just querying the backends. Litmus Paper is responding with the healths. And then based on Big Brother rules, the load balancer will forward or not forward traffic to those backends. So it's pretty straightforward. OK, so that works really well for stateless services, things like Apache, where you can send traffic to 3 different Apaches. And then if one goes down, you just send it to 2 Apaches instead. We also have a class of stateful servers where you can't just send all of your traffic to all of them. So load balancers are one of them. The virtual IP lives on one load balancer. Postgres is another big one. So we have primaries and standbys. You can't send all of your traffic to all of your Postgres servers. You need the writes to go to the primaries. If you try to send writes to the standbys, you'll get errors. So for these, we use Pacemaker to manage failover. So Pacemaker just kind of manages a cluster of things. So it manages a cluster of our Postgreses. It keeps track of which one's primary, which one's standby. If the primary fails, Pacemaker will do the failover for us, and it'll promote the standby. And then we just move virtual IPs. So the app just knows the virtual IP of the database, the virtual IP of search, the virtual IP of pretty much everything. And then when things die, either they'll unbalance or Pacemaker will move them. And then the virtual IP just moves along with it. So we don't need to reconfigure anything when things die. OK, so that's server failure. Now we have network failure. So fun site to look at, internetpulse.com. It shows you basically outages between different ISPs, internet service providers, across the internet. So I took this screenshot last week. It turns out that issues in ISPs are actually very common. So you can see at the top, you can see the red box is between CenturyLink and Savvis. So if you're running a service on Savvis and you're trying to connect to it from your home, which is CenturyLink, let's say, you might have trouble connecting. You can see there's a lot of ISP issues. One of the things I learned at Braintree is that it's network issues are actually very common. It's amazing sometimes that the internet actually works. Because there are so many issues just with connections across the wire. So pretty much if we see connection issues, we'll pull up this site. And you can we know which ISPs we serve out of which data centers. And you can kind of look at the different connection issues with other ISPs. OK, so we have two kinds of networking I want to talk about here. So the first one is inbound. This is a merchant wants to charge a credit card, so they make an API call to us. So that's inbound coming to us. So for that, we use BGP to route traffic through multiple ISPs and data centers. So BGP is the Border Gateway Protocol. It's essentially the protocol of the internet. So it uses DNS to go from a name to an IP address. So BGP is how you figure out where to go with that IP address. So our routers participate in BGP. They broadcast the IPs that we handle. And then BGP handles finding the best path through the internet to get to us. So if an ISP goes down, BGP will essentially unbalance it, and then it'll find another route to us. So in general, BGP does shortest route. With some caveats. But if the route is down, it'll find a new route that's the one that's up. So by participating in this, we have multiple paths coming into us. So depending on where the merchant is, where the customer is, the traffic will route to us via different ISPs and different data centers. And then we use monitoring services. We use Pingdom pretty heavily, and we use our own kind of servers that we scattered throughout the world. And we basically just do that to monitor it. So BGP is great. It unbalances. It works. But it's not always instantaneous. We've seen issues where, especially when ISP outages are partial, we've seen issues where we see a lot of problems coming in via one route, but BGP hasn't figured it out yet or hasn't fully unbalanced. So since we have our own monitoring, we can kind of detect these cases, and then we just manually yank the BGP routes and force the traffic over a different path. So that's kind of how so BGP generally does its own thing, it works, but we also can do it manually if we need to, based on our own monitoring. OK, so that's traffic coming to us. We also have the problem that we are not the endpoint for most of this traffic. We need to go out to the processing networks to actually tell whether their credit cards are valid or whether they have enough money on them. So in general, we don't talk to Visa directly. We talk to what are called merchant providers or processing networks in general. So for people that know payments, we talk to Chase Payment Tech, TSYS, First Data. We talk to internationally. We talk to a lot of banks directly because we need to get back to whichever issuing bank issues a card and knows the balance. If you have a Chase credit card, we need to talk to Chase to know if you have money on that credit card. So like I said, we integrate with a ton of these processing networks, and we need to basically make outbound calls to them. So you make a call to us, we need to turn around and make another call to figure out how much is available on this card. And so like I said, so ISP outages are usually partial. It's rare that you have a total outage. It does happen. I think last year there was some construction in Chicago, and they just drilled right through the line, one of the big ISPs in Chicago, and took out the entire thing. But generally, a router fails somewhere, or there's some packet loss. So they're not usually full outages. So we've gotten into cases where we have multiple ISPs, but we can't reach every endpoint we have to hit on all of our ISPs. So it's not like we can say, oh, we're having problems with this one. Let's just take it out. We'll use the other one. Maybe they're both having partial outages, and we can only reach some on one and some on the other. And so what we really wanted was a way to choose an ISP for the endpoint we're trying to get to. So some are better than others for certain paths. We want to use the best one for that path. And so what we built are processor proxies, is what we call them. So instead of the dispatcher connecting directly, we connect through a proxy. we run one proxy per endpoint, so per processor, like we run one for Chase, let's say, pinned to a specific ISP. And then we can load balance over them. So if there are issues, we allow our load balancing to take them out. And this allows us to route around issues on ISPs that are partial, essentially. So the piece we wrote to do this is called Mallory. It's also Python Tornado for the same reasons. It's just shoveling traffic back and forth. We want something very lightweight. It proxies requests. And this is a big one. So we looked around. We didn't want to write our own proxy, but we kind of looked around what was out there. And SSL verification is kind of a big deal. So SSL does encryption, but it also does verification, which is you want to know that the endpoint you're connected to is actually who you think it is. So most of the processing networks use SSL, and a lot of proxies will do SSL encryption, but they don't actually do verification. So they'll ensure that your traffic's encrypted, but not that you're connecting to who you think you're connecting to. And so one of the things we do is we strongly verify the SSL certificates, so we can't get man in the middle. So if somehow we were to get man in the middle upstream, our request would fail rather than send credit card data to the wrong person. And then we would notice that our requests are failing, and we would look into it. So it's really unfortunate that if you look online and you kind of Google this, a lot of recommendations online are, oh, just turn off SSL encryption, right? curl-k, like just turn it off. But I mean, SSL is very powerful, and you should definitely use it as much as possible, even with verification. So the other cool thing with Mallory, and another reason we wrote it, is it acts like litmus paper. So the same way Big Brother is querying litmus paper, Big Brother can directly query Mallory. So Mallory is doing the proxying, and it's keeping track of how that proxying is going. And then if the last few requests haven't gone so well, when Big Brother queries it, it can say, like, actually, proxying's not going that well. I'm going to return a low health or a 0 health, saying that this route is just not good right now. And Mallory is also open source. You can check it out. So this is kind of what the diagram looks like. So the dispatcher is trying to make a call to the processor on the right. It makes a call through a virtual IP that's load balanced over 2 Mallories. Each Mallory is pinned to an ISP in that data center. And then the traffic will eventually route there. So if the ISP 1 goes down, the top Mallory will unbalance, and traffic will flow through the bottom Mallory. And this works. When we look at the logs, we see Mallories kind of unbalancing periodically throughout the day. Like, little issues will happen, but we generally survive them without really noticing. So connection failures. We do get connection failures, right? The way we know that a route is bad is we will get a connection failure trying to talk over it. So this is something we do have to deal with. Our general practice is we just let things heal. So in the case of Mallory, we get a connection failure. We know that when Big Brother goes to query, it will unbalance it. So we just let the system heal. With things like the database, we know that Pacemaker will handle the failover. So we just wait. Like, we just wait for it to handle the issue, and then we retry. And we do retrying at a lot of different levels of our stack. So in the case of processor calls, we'll often do several, 2 or 3 if we can't connect, knowing that if there's an issue, Mallory will unbalance, and then we'll reroute around it. With things like the database, if our primary database were to crash, we would lose the request in flight. There's not much we can do about that. But before our dispatchers pick up another request from Redis, they do heartbeats. And so they won't pick up a request until they can actually check that the whole app is working again. And that means that the database has to fully fail over, the new one has to come up, then the heartbeats will start working, and then the dispatchers will pick up the request again. And so this is the way we kind of retry there. So we won't pick up requests if we know that things are busted. We'll wait until things have healed and then start processing again. OK, so just to summarize kind of the unplanned failures, load balancing we do for server failure and also kind of components of network failure. We have redundancy across ISPs. Inbound, we use BGP for routing. Outbound, we use processor proxies to kind of target the right ISP for the right endpoint. And then in general, we just let things heal and then try again. And we do, like I said, we do retrying at many different levels of our stack. OK, so the last section, people make mistakes. It's inevitable, right? People can cause outages. You run the wrong command, you do the wrong thing, you cause an outage. People can also make things worse. Let's say there's already an outage and you just take a long time fixing it. Or you run a command to try to figure out what's going on and you just make the outage worse. So people can be a problem. So here's a couple examples. The big EC2 outage of 2011, they say that the traffic shift was executed incorrectly. So you know that someone there just probably ran the wrong set of commands. GitHub outage, also a few years ago. This one, due to a configuration error, they accidentally dropped their production database rather than their test database and had to then go restore their production database from a backup. And I believe they were down for a good chunk of that time. So that one, they just ran the wrong command in the wrong environment. PagerDuty had an outage this year. This one's really interesting. They actually call out, due to the engineers being extremely tired and burned out after working through the night on the upgrades. So this is very common, right? You have an issue, you're working on it all night, you're just more likely to make mistakes once you're tired. And I don't mean to call out these companies. I think it's great that these companies are so open that they can publish these postmortems and that we can all, as a community, learn from it. My point is just that every company has people issues and everyone will make mistakes at some point. So the goal is just kind of reducing these mistakes. You can't entirely prevent them. So we just want to reduce the factor. We know we can't get rid of it entirely. So one of the big things we do is we automate everything or as close to everything as we can. So automation reduces errors, right? Like if you're running an automated command, it's less likely you'll forget the wrong command line flag or something dumb. You're more likely to run the right thing at the right time. It also gives confidence that things still work. So like I said, we're a fast-moving company. Infrastructure's changing. Maybe the way you unbalanced a service a month ago isn't the same way you unbalance it today. Maybe the set of commands have changed. If you rely on automation, then when things change, the automated tasks will change. And then you know that when you run the unbalance command, it will do whatever the right set of things are today to do the task you want. So over time, you know that it's going to do the right thing. And you don't have to worry about, hey, what's the way I do this? How do I do this today versus how did I do it a month ago? And then in general, it just speeds things up, right? We have these proxy pauses for 20, 30 seconds. If we have to do a lot of work in there, like complicated failovers, we don't want to have the person typing commands and hitting enter. Like we need to run those very quickly, and automation just takes care of that. Just in general, like the less you're in production, the less likely you are to make a mistake. So automation means less time in production. And our tools are Capistrano and Puppet. So we use Puppet to manage server configs, so we know that every server is set up the same way or in a consistent way. So you know that the unbalance on one server is the exact same as the unbalance on another because both boxes were set up with Puppet. And then we orchestrate everything through Capistrano. So all of our deploys, all of our failovers, unbalancing, we pretty much have tasks for pretty much everything we want to do in production and in all of our environments, really. OK, so besides automation, we also add a lot of safeguards. So one big one is dangerous tasks just don't run in production. So if you want to drop a database like you would do in test all the time, you try to run that in production, it just fails. It says, like, we use the environment to know, like, you can't run this in production. It'll just blow up on you. So we try to prevent, the GitHub issue of dropping the wrong database. And so we have lots of dangerous things like this that just won't run in certain environments. We also add the environment name to the prompt. So on your terminal line, you're typing commands. At the beginning of your line, it says in red letters production. Or if you're in a test environment, it'll say in green letters test or something like that. So as you're typing commands, you're looking right where you're typing. You see in big red letters production. So you know exactly what environment you're working in. And this is really helpful when you're working in multiple environments. Maybe you're testing something out in test, but then running it in production. You're switching back and forth. You want to know which ones are in test and which ones are in production. And we just put that right in the prompt. We also have read-only databases and logs. So if you're interrogating something, trying to figure something out, you don't have to worry about accidentally running a bad query. One, you're read-only, you can't destroy anything. And two, you're doing read-only on a database that's not even in the main database, in the data center. So even if you were to run a query that didn't modify anything but was super slow and brought down the database, like you don't have to worry about it. Same thing with logs. We look at logs on log servers that are shipped out of our main center. So if you were to run a really expensive grep and slow down the box, like you don't have to worry about actually slowing down production or anything like that. So we basically just try to shield you as much as possible from the actual running software. And then the other thing is monitoring. So we use Nagios pretty extensively. So Nagios monitors everything from like the load on a box, uptime, to we write a lot of custom checks, like did the nightly settlement job finish successfully? Did we bill all the subscriptions that we were supposed to bill? Did we miss any? Things like that. We have a lot of checks just at all levels. We have that hooked up to PagerDuty, so it'll call you. So if a check fails, it calls you. So if you're working in production, you generally have Nagios open, and you have PagerDuty set up to you. So if you do something and something goes wrong, you immediately get a phone call, and you know that you did something, and you're right there ready to fix it. And then we also have this multi-app log tail. So our general way, we use tmux. We split vertically. Generally one side is the commands you're running. The other side is just a log. And we have a script that takes the logs from multiple apps, puts them together, strips them down to just the important parts, and colors them. So you'll see like greens for HTTP successes, reds for failures. We also color it by response time. And we show the total time and the app time separately. So you'll know if the total time is really high, but the app time is low, there's a queuing issue. And we just have this thing kind of scrolling. And because our apps are pretty busy these days, we added sampling. So maybe you only want to look at 3% of the traffic, just so it's a reasonable amount. And you see these logs. If you're doing something and all of a sudden you see red out of the corner of your eye start to go, you know you did something wrong. You're right there. You can fix it very quickly. You don't have to wait for something else to happen. So like I said, you can't always prevent the error, but the idea is catching it really quickly and trying to fix it before it becomes a really big issue. And then we use Graphite and Munin for graphing. We started with Munin. We're moving most of our stuff to Graphite now. We don't really alert on this stuff, but it's more like if you're doing some kind of work. Let's say you're running a big database load. You'll pull up the graphs for like the database I/O and the database boxes, and you'll kind of watch them. So if you see crazy spikes, you know that probably something's wrong, and you can act on it. So this is more just like you know you're doing something, and you want to watch it. We also have dashboards in the offices and stuff like that. But just you want to keep an eye on what you're doing so that if you do cause a problem, you can find it very quickly. And that's pretty much it. So to summarize that, just automation, pretty much automate everything, reduce errors. With safeguards, just to try to prevent people from doing the wrong thing as much as possible. And when you're running commands, to know the environment you're running them in. And then just as much monitoring as we can. We have the monitoring that happens at night so that you get a call if something fails at night. But then also just keeping an eye on the monitoring while you're doing work so that you know if you cause a problem. And that's it. Thank you.